are looking at, that is the fluid flowing down an inclined plane. This is the direction of the fluid. So we assume we have one-dimensional flow, right? And as a result of that, the flow and pressure profiles were obtained as follows. So we saw how the forces act on, let's consider a rectangular volume element centered at, let's say, x0, y0, and z0. We look at the contact forces that act on the body of fluid. So we have to consider the 6 faces, on each one of which the normal is oriented in a different direction. So we get E of EA is said, for instance, if you take the top face, right, we saw that N is equal to EX, and so T itself will simply be N dot T. So this is the most important formula. It gives you, you've already seen, given that we know how to construct the stress tensor. Stress tensor in this case is minus P. Right? So that's how the stress tensor looks like. So given the velocity profile, we can easily calculate mu times dz by dx. So this is how we will calculate. So that N is equal to Ex, we saw that the T, the stress vector, would be Exx, Ex. This is 0. Ex, so it has components on both the directions. Ex as well as Ez. This will be the normal force, and that will be the tangential force acting on the z direction on this top face. We just take the top face. So now we have to integrate this. So the normal, we have given a general rule for calculating the normal of any surface. It need not even be a plane surface. Right? We simply have to express it as using x, y, z. And then we have to calculate the gradient vector, and then we have to take the unit vector corresponding to that, and we will give the direction. We can do that. So the coordinate surfaces, for the coordinate planes here, it's either Ex or minus Ex, or Ey or minus Ey, and Ez or minus Ez. So that's very easy. But the problem will come when you integrate. Let's say I have a surface, and I want to integrate it, because the stress vector may vary from point to point. So if you want to integrate, then we need to know what to do with this EA. That's you're doing an integration, it's an area integration, but in 3-dimensional space. Right? So that's a little bit more tricky to do. We'll do that later. But here there is no problem, because we are only considering the surfaces to be the coordinate planes. It's very clear that this coordinate plane, right, the area element, the normal is Ex, while the area element is simply given by dy dz. Right? So that is how we have to integrate. So the integral would then be Exx is minus Ex plus, it's important that you look at this as different components. It's not just adding, because you have the vector here, so the easier way is to Ex and then minus PDA plus Ez times dxz dz by dx dA. Right? So what I see here is the dA now can be replaced by dy dz. dy dz. So there are actually two integrations. And y varies from y0 minus delta y by 2 to y0 plus delta y by 2. And similarly for the same limits hold for this also. What I find here is since the pressure as well as the velocity and hence the gradient of the velocity dependent only on x, right? The integral is independent of y and z. So you can simply write this as dy dz times minus p. We know, but important thing to remember is that the location of all points, which is what it means, the location here is given by the x value for all the points is the same. And that's the simplification that you get. So we have minus p evaluated x0 plus delta x by 2, right? And then plus evaluated at x0. This would be the ex component. This would be the ez component also. This is delta y delta z. So this is what we would get. So constant, the integrand is effectively constant, but it has to be evaluated at x0 plus delta x by 2 for the top phase. For the bottom phase, right, it would have to be evaluated at the x0 minus delta x by 2. So effectively what you will get is minus the x component would be right, minus, it would have a negative dA plus rho d sine beta times delta minus x. That x is x0 plus delta x by 2. This would be the dx component. Ez, to calculate mu dz by dx, that would be rho g cos beta cos beta times delta minus x. So that's what we get. Now if you look at the force acting on the bottom face, for the bottom face n is equal to minus ex. So we would have effectively the same. So t would be actually minus of dxx, dx and so on. Right? T would be that. And the integral would again be simplified because again there is the integrand would be a constant. The integrand would have to be evaluated. This would have to be evaluated at x0 minus delta x by 2 rather than x0 plus delta x. If you combine the two, then you will get that the force for top plus bottom, contact force, is equal to rho sine beta dx minus rho g cos beta. The whole thing is actually proportional to the volume of the element that we have chosen. Now the problem will become slightly more complicated for the left and right phases, because in those cases we need an integration, because the integral is for those, for instance, for the left phase, right? For the left phase, if you see the normal, the outward normal would be Ez, right? The area element dA, for which I have to integrate, right, would simply be dx times dy, corresponding to the integration. So the integrand, we know is a function of x, so it has to be integrated. The integration over y would simplify. You get a delta y. The integral over x would have to be done from x0 minus delta x by 2 to x0 plus delta x by 2. The whole thing, this whole thing has to be integrated now from x. It's not evaluated at one point, because it varies from point to point. X varies over that phase, right? But you will find that the forces on the left and right phases, the net contact force, I want you to derive it and verify. The answer is correct. You don't even have to integrate out the full expression. By just doing the explicit in terms of the integral, you can easily verify the left plus right phase together. The contact force is 0, and similarly the front and back phase, if you take them together, the contact force is again 0. The net contact force is, you have to verify that. I want you to verify that you can calculate the integral for each and every case and then cancel out. Or you can simply look at the integral. You have a property of integrals, and if you have integral a to b in one case, you probably have minus a to b or b to a or something like that, right? So you can easily verify that the terms would cancel each other. So this would be the net contact force, and the whole volume element is actually given by this. Right? Now, another method was suggested, because we know that integral is nothing but integral n dot d dA. This is what we used to calculate this. But we saw also, when arriving at the equation of motion, we can express this as a volume integral, which would begin the divergence of the stress tensor. So this can also, this would turn out to be easier to do, right? So, but anyway, this exercise is still useful, because you get to know how to calculate the force on any, at least integration you can do over a coordinate plane, either the xy plane or the xz plane, the yz plane, because not only what you need is a normal, we also need to know how to do this integration, A, right? You handle for the general, either planar or even curved surface, how to do that later, right? But right now, right, you can avoid this integration completely by simply calculating one integral, and that is the over the entire volume. So what I need to know is the divergence of the stress tensor, right? So if I want to calculate the x component, so x component would be dV. The y component would be, and the z component would be. So I have to verify that the x component is in fact given by this, and the y component is 0. The z component is given by minus rho t cos beta. So how would you calculate now the what is equal to, can you write, what is the x component of the right? Now 1, 2, 3 is now becoming x, y, z. So you can write it in terms of 1, 2, 3 and simply make the transformation 1 to x and 2 to y and 3 to z. It will contain 3 terms, right? So for general x, this would be x. The other 3 will vary from 1 to 3. So it would be y, x, y and z. So you get 3 terms. It's very easy to make this transition. 1, 2, 3 to x, y, z. So let's see. You've already done it. Okay, fine. So this is dxx with minus p together. Right? This is dzz. Right? So complete the what is minus p? E by dx. That's why I mean it's important to not jump steps and do it properly. Otherwise you will just give the impression of manipulating some symbols which have no meaning. Right? So this is where you go ahead and evaluate. So this would be, you want to write it properly because the gamma j represents derivative with respect to xj. Here it would be with respect to x, y or z. So that would be d by dx, dxx plus d by dy, dxy. dxy is 0. Right? d by dx of dxx is what? Time because it's just one term. VA was rho d sin theta and delta minus x. So automatically you will get rho d sin beta. What are you doing? Delta minus x. No, how do you get delta minus x times? I don't know what you have done, but clearly it's just to fixate this with only one term. VA will not give anything. When you differentiate the constant, rho d sin beta times delta is not going to give anything. So you can read off what the derivative of that as to be minus rho d sin beta. So minus dt by dx is rho d sin beta. Other terms are clearly 0. There is no variation with respect to z. Right? The only contribution you are getting plus rho d sin beta. That's exactly what I have to do. I already recommended the x component. You can go back. Now it's very easy to do the others. Y would simply be, I don't want to do it here. Right? So I take this to be y. Earlier what I wrote was for x. When I write for y, right? Everything is y. I'm sorry. And z y. Right? dxy. Right? dxy by dx. dxy itself is 0. So that term won't contribute. dyy, right, is of course minus p. So you should know what is vanished, why it is vanishing. dyy is not 0. dyy is minus p, but it doesn't vary with y. That would be 0. dzy is 0. So that is also 0. So as we expect, the y component would be 0. So this is then the divergence equal to 0. So what about the z? So I'm using the same formula, but I make it z. So the second index is z. That's all I have to change. Right? So now dxz, of course it varies with x. That's the only non-off diagonal component. But first let me eliminate the others. dyz is 0. Right? dyz is 0. dzz is not 0, but it's very by dx of that, of the component. So that is simply mu times d squared dz by dx squared, which would be very easily shown to be, right, what would that be? So you have already formula for mu dz by dx. I just have to differentiate it again with respect to x, and that is turns out to be again 2 delta x. So this term won't contribute when I differentiate twice. So only contribute is coming from minus x squared. If we differentiate it once, I get minus 2x. If I differentiate it again, I get minus 2. That's the only x dependence. Minus 2 times this will cancel with 2, and I will simply get minus, and so I conclude that minus, sorry, the also cancel because I have a mu here, right? These cos betas are all length again, and that's exactly what so all the when it comes to the volume integral, the integral is constant, right? Because what I have here, of course, this is now dx, dy, dz. The integral has 3 components. Ex I have is rho d sine beta. The x component, the y component is 0. The z component minus rho d cos beta, right? But all of them are constant. They are independent of x, y, or z. So we simply get delta x, delta y, delta z times the same quantity. So we verified what the divergence theorem says. It's been verified here. Clearly, you can compare, even if I might have to go through all of it. Just want the total force on this, right? Then clearly going through phase by phase and calculating TDA is not the approach. If I, however, ask you to calculate the force on any one of those planes, then you have to do the individual calculation. But we want it on the volume element, the body of volume that I have taken, right? Then it's clearly easier to do the volume integral. In this case, at least, it's very easy to do, right? So this also demonstrates the use of the divergence theorem to simplify your force calculation, right? Now you can ask, this is only the contact force. What about the body force? The body force, right? Integral OP dV, right? And here the inclined plane, right? G is, we have to be careful about G. This is the G that is acting vertically down. So it has to be resolved, right, as G minus G sine. We have already seen this. We have written the body force components, right, in the 2 directions. X and Z only will come into play. So this is G cos beta along the Z direction. Because the direction of fluid is d times cos beta, so rho b dV would be rho times G minus G sine beta Ex plus G cos beta Ez times dV. So again the integral is a constant. The integral over volume is simply going to be the volume itself times, delta x, delta y, delta z times minus rho g sine beta Ex plus rho g cos beta Ez. So we see the body force is simply the negative of the contact force. The total force is the sum of the body force and contact force. We get that the total force on the volume element is actually 0. volume element, at least the one that we have considered, the net force is actually zero. Is this the correct result or there is a mistake in the calculation? Right? Constant, not a constant velocity. Velocity actually is varying in the flow direction, right? So, if I simply wanted the total force, right, I need not have done any of these calculations because I know that the total force is of course given by dEA plus dV, which can be written as nothing but what is this integral? How else can I write this? Divergence of the stress tensor plus rho times the body force per unit mass. What is that equal? Rho dV by dt. We've just seen that for the one-dimensional flow, a steady one-dimensional flow, the inertial terms vanish identically, right? So dV by dt is actually what you may call actually capital D by dt of D is identically zero in this case, right? So if I wanted the total force on the whole body element, I need not even have calculated the individual contact and body force, but I simply noted the equation of motion which says that the total force on any volume element has to be actually zero because dV by dt, I will see as dV by dt plus this is zero because we are considering a steady flow. This we have shown for the one-dimensional special case. The inertial terms we have shown identically vanish, and because of various factors. Because if two of the velocity components are zero, the variation of Pz along Z is zero. So that will give rise to this. So if I wanted the total force, I could have simply directly gone to this and concluded that the net force acting on the volume element would actually be zero from the equation of motion by simply looking at the left-hand side of the equation. What I looked at, when you talk of force, you immediately look at the right-hand side, and we have done that. Right? But it's still instructive to go through this exercise to verify what we may have inferred by just looking at the equation of motion for this case. Right? But it's still important because what we have seen if you do the top phase, I've done the simplest part. If you look at the bottom phase or the front phase, you will see that it requires a certain integration. If you go and do the integration, at least for the simple case, there is just only one integration that you have to do, namely with respect to x. So it is still important for you to be able to calculate. If I simply ask, let's say, consider a rectangular, you will just calculate the force on the front face. Then obviously there would be a net force on any one of the 6 faces, and you would have had to do the calculation. It's important for you to know how to calculate the force on contact force on any surface, particularly we have considered the planar surfaces. Then we have also shown how the divergence theorem can be used to simplify the calculation for a given body of fluid. Right? We have also seen the importance of recognizing the equation of motion and how in this special case it makes the net force on any volume element to be zero because this is an acceleration-less flow. Are there any questions? Okay, we consider another simple example. I just want to write down the results before we move on to discussion of the curvilinear coordinates. Another standard, 3 or 4 standard examples that are used for illustrating the application of the equation. So we've gone through the whole procedure. We've written down the equation of motion, simplified it for the one-dimensional case, calculated the velocity profiles and so on, constructed the stress tensor. Each and every step is important, right? Constructed the stress tensor, saw how to calculate the contact, which is the most important important because the body force is very simple. In this case, contact force can also be considerably simplified by using the divergence theorem. But body force is not of much importance. Right? In terms of calculation, it's not as complicated because this is what we have to deal with the stress tensor and know how to calculate the stress vector and how to integrate it over the surface. Right? We've seen that. So you should know how to do all this. Right? So we now consider another example. So I'll combine these 3 or 4 examples. For this one we have done comprehensively, but we now consider a flow. 2 or 3 other examples that I put together in an assignment and give it to you so that you can solve it, after your quizzes are over. So, flow between parallel plates. So this is there are 2 plates here. The only complication that would arise is typically we consider one of the plates to be moving, and so that will create some scope for analysis. So what we are having is, again, we assume a one-dimensional flow. Continues and take this to be the z, this to be x, and this to be y. So that the direction of flow is the same as what we had in the earlier case. Right? So I now assume that this one has a height capital H, the height, the distance between the 2 plates. So we assume here between B z equal to B is rather equal to. This would automatically mean that B z is to continue the equation is a function of x and y only. We'll further assume that B z actually has no variation along the y direction, very similar to the previous case. We'll assume, make that assumption. Then if you write I'm just going to quickly go through the continuity equation will simply give dBz by dz equal to 0. That's what it will give. The momentum balance, the y component, would give dP by dy equal to 0, which means P is a function of x and z. And if you write the x component, you will get minus dP by dx minus rho g is equal to 0 because the gravity is acting in the negative x direction. You have the gradient plus the body force, which will simply be minus rho g. There will be no other components of the body force. Right? So this can be very easily integrated. We already know that P is a function of x and z only. Right? So this can be integrated. So minus dP by, rather dP by dx is minus rho g. We integrate it and get P equal to minus rho g x plus what? Plus some function of z. So it cannot be a constant in the most general case, and it will invariably here develop which I call some P naught of z. Now, if you look at the equation of motion in the third coordinate, that is the z coordinate, you get minus dP by dz is plus so that will begin the viscous term, much like what we had in the falling film case. Now, if you look at minus dP by dz, if I differentiate this with respect to z, this term will not contribute. So minus dP by dz would simply be minus dP naught by dz, right? So I can write this. This would mean that mu times d square dz by dx square is equal to dP by dz. dP by dz is simply, I'll write it as P naught prime z, where prime denotes d by dz. Of course, dP by dz is a function of both x and z. special case, dp by dz, it has two components, one dependent only on x, one dependent only on z. dp by dz would be p naught prime of z. So if you look at the two sides of the equation, this is actually also only the, we don't need the partial derivative. So what we have is right? What we have is this. Now a standard argument follows that we see that the left hand side is a function of x alone, the right hand side is a function of z alone. So the two must be equal to a constant. An argument you must have made in when you do for the separation of variables, right? You split it into two parts. You have x and time, let's say, single variable and time. To avoid the separation of variables to the actual partial differential, you get two ordinary differential operators, right? One a function of time and one a function of x, and you equate the two, and then say this two has to be equal to some lambda squared or something. That's a standard argument, right? So otherwise you cannot have one being a function of x alone equal to something which is a function of z alone. X and z are independent variables. Only way it can happen is that it is a constant. So what we get here is that the p naught prime of z is a constant. So you simply write it as here, as opposed to the earlier case, the p naught prime, the dp by dz, that's a constant, right? So I simply call this as p naught prime. So now we come to the, so it's very easy to solve this. So we can solve it once, we integrate it once and then integrate it again. We get as the general equation. So I integrate it once, I get p naught prime x plus c1. I integrate the second time, I get p naught prime x squared by 2 plus c1x plus c2, right? That's the general solution. Now, if we want to find the constant c1 and c2, the second order equation, I need two boundary conditions. And here, as a standard case, is to assume that the bottom plate is stationary and the top plate is moving with the velocity u, which may actually be either greater than 0 or less than 0. If the plate is moving in this direction, right? The plate is moving in this direction, then it is positive. The plate is moving in that other direction with a magnitude u, then it would have to be taken as u to be negative, the vector, right? So now we have this, so I leave it open at this stage. So we have that at x equals to 0, Vz equal to 0, x equal to h, Vz is equal to u. Whether u is positive or negative, we worry about it. The Vz is, B is, what we are looking at B actually, right? So we have to be clear about the direction in which the plate is moving also. So if you do that, then we get the solution to be given. We have to discuss this in detail tomorrow, but I will just write down all these steps. If I rush through, you have to look at the equation of motion and verify whether I have written them correctly, and then getting the solution, and then arriving at finally this as the p naught prime, the negative of that as one term. You can see why that is. P naught prime is a constant. It's actually dp by dz. It can be positive or negative, and then we see what it means. Now we get two parts to the solution. There are actually superposition of two effects. If now P naught prime is 0, then I get this very standard solution of V to be just Ux by H. Right? So that profile is very easy to plot. P naught prime equals 0. Let's assume that U is moving in the U is moving in the positive Z direction, then the profile would look like this. This is U. Very simple linear profile. On the other hand, if U is 0, right? If U is 0, then we get the parabolic profile. X, I've written it as. If you look at this, if you just for the moment forget about this, that will vanish when U is equal to 0. And when U is equal to 0, so X is positive, H minus X is positive. Clearly we see there will be a flow in the positive Z direction. If P naught prime is actually negative, that means there is a pressure drop in the Z direction. That's what we, it's a pressure driven flow. If you now compare, just forget about this term for a moment, U equal to 0, right? It will vanish for U equal to 0. Now comparing with the earlier case, the falling film case, very similar, right? This may be what is called as a pressure-driven flow. So there is no gravity that's driving the flow. The earlier case, if you saw, there was no pressure gradient in the flow direction at all. In spite of that, P was very only the X direction, and effectively turned out to be the hydrostatic pressure. Right? There was no variation in the Z direction. Right? So the flow was still possible because of the effect of the gravity. So this is the complement of this. This is a. So here gravity is not driving the flow. It's actually normal to the flow. It's not contributing anything to the flow itself. In the other case, you have to recall that there was no variation of the pressure in the flow direction. Yet flow was possible because of the effect of gravity. That can be called as a gravity-driven flow. And this is a pressure-driven flow. So if there is no movement of the plate, then you can have flow only when there is a pressure drop in the flow direction. That's what it says. Right? So now you look at it, how will the profile now look like? So if you look at all possibilities you can consider things. Consider P naught prime to be, greater than 0, then the flow will be in the opposite direction. So we won't introduce too many complications. For all our calculations, we consider P naught prime is less than 0. So I know which direction the pressure is driving the flow. Now we can consider, this is our standard conventional analysis. I can now consider the effect of U. What happens to U? So I'll consider two cases. Case 1, when U is greater than 0, that means the plate is also moving in the direction of the pressure drop. Right? Then what will happen? So what will now happen? So we have seen how there is no pressure drop. So we are considering now the case where U is greater than 0. So this will be the profile when the pressure drop is 0. Right? Now what will happen when you combine the pressure drop? So we can easily draw what will happen when U is 0. In the parabolic, you have a maximum at what value? And x equal to h by 2, just as we have the parabolic velocity profile in the flow to a cylindrical tube. Now you can ask, so those take care of the two independent cases. When you combine the two, what will happen to the velocity profile? We see that in tomorrow's class.